For the last 3 years, the entire generative AI industry has been basically relying on a mathematical trick to save compute power.
Yeah, pretty much.
But that trick is actively destroying the exact high-frequency details we are trying so desperately to generate. Welcome to AI Paper Slop. Today, we are analyzing the comprehensive survey paper, Pixel-Space Diffusion Transformers, or pDiT for short by Yan and colleagues.
Right, a really crucial paper right now.
Exactly. And look, if you are building generative models right now, you know that latent diffusion models like stable diffusion have totally dominated the landscape.
Oh, absolutely.
And they do this by using a variational autoencoder, a VAE, to compress massive images into a tiny latent space before the actual diffusion process even starts. But here is the core unvarnished insight from this paper. That two-stage compress then diffuse paradigm has hit a rigid physical performance ceiling.
It really has.
It creates this irreversible information bottleneck that just obliterates microtextures, it ruins text rendering, and mangles minute local structures. So what this paper details is a massive algorithmic renaissance taking place right now.
Yeah, total shift.
The industry is returning to the raw pixel space. Powered by scalable transformer architectures, modern pDiTs are entirely eliminating the VAE bottleneck to jointly optimize both representation and generation.
Which is huge.
It unlocks extreme high-fidelity outputs and establishes a true shared token foundation for unified multimodal models across vision, language, and beyond. So if you're an ML engineer, you need to understand exactly why the industry standard is suddenly pivoting back to the very computational space we abandoned just a few years ago.
It is a massive pivot. I mean, and to really grasp the mechanics of why this shift is mandatory right now, we have to contextualize how we got back into this corner in the first place.
Right.
If you look at early denoising diffusion probabilistic models like the original DDPMs, they actually did operate directly in the native pixel space.
Yeah, they started there.
Exactly. But, right. The VAE is optimized purely for reconstruction. It is designed to act like a compressor, so it actively discards local variations, subtle lighting shifts, noise, microtextures that it deems mathematically unnecessary for the broad strokes of the image.
But the diffusion model wants those details.
Exactly. It's optimized for generation. It wants to generate those microtextures. When you permanently separate representation learning from diffusion training, you introduce a fatal flaw. The latent space becomes a highly compressed black box that entirely obscures internal geometric and semantic configurations from the diffusion model.
Okay, let's unpack this, because I think a lot of people assume it's just like a mild degradation. It's sort of like converting a perfectly lossless FLAC audio file into a highly compressed MP3 to save processing power.
That's a great way to think about it.
Right. To a casual listener on cheap headphones, it sounds perfectly fine. But when a downstream machine learning model tries to isolate a very specific high-frequency instrument from that MP3, the data isn't just hidden. It is literally gone. Gone. You cannot reconstruct what the compression algorithm mathematically discarded.
That analogy works conceptually for sure, but the visual equivalent is actually far more destructive.
How so?
Well, when an audio file clips high frequencies, you lose crispness. But when a VAE compresses an image into a latent grid, it actively smooths and scrambles spatial relationships. The loss of data manifests as distorted local geometry.
Oh, which is why models historically struggle with hands.
Yes. Exactly. It's why we see degraded sharp edges and those weird hallucinatory artifacts when models attempt to render small text or highly regular patterns like brick walls or chain link fences.
Because the data was trashed.
Right. The downstream diffusion model simply cannot recover fine-grained information that the fixed visual tokenizer threw in the trash during step one. It fundamentally prevents us from doing end-to-end large-scale model co-design.
Which sets up the brutal reality we are facing today. Because if we throw away the VAE and return to raw pixels to get all that beautiful high-frequency data back,
we hit a wall.
Exactly. We immediately run face-first into the exact same mathematical compute barrier that chased us out of the pixel space in the first place. So, I mean, how are we defining the generative trajectory now, and why does returning to pixels completely break standard transformer architectures?
Okay, so to understand the bottleneck, we have to look at the two theoretical frameworks currently driving pixel space generation.
Okay.
First, you have the traditional DDPMs. These rely on discrete time Markov reverse diffusion chains. Essentially, they track conditional probabilities, progressively peeling away Gaussian noise step by step, almost like walking backward through a dense fog.
Got it. And the newer approach?
The newer approach relies on flow matching frameworks. These are deterministic, continuous flow frameworks. So instead of taking discrete probabilistic steps, flow matching learns a time-dependent velocity field.
So it's smoother.
Yeah, it basically builds a continuous mathematical river that seamlessly transports samples from a standard Gaussian noise distribution directly to the target image data distribution.
But here's where it gets really interesting for the engineers listening. Because regardless of whether you use a discrete Markov chain or a continuous velocity field, you still hit a catastrophic scaling crisis.
Oh, absolutely.
Because we aren't using convolutional networks anymore, right?
Yeah.
We're using vision transformers. And transformers operate on sequences of tokens. So if you keep your patch size fixed, say, every token represents a 16 by 16 grid of pixels, and you increase your image resolution, the number of visual tokens, which we represent as n, grows quadratically.
And this is where the algorithmic reality becomes so unforgiving, because standard global self-attention mechanisms require every single token to explicitly model its relationship with every other token in the sequence.
Which is a nightmare.
Total nightmare. The time complexity for that global attention computation is big O of n squared times d, where d is the feature dimension.
Wait, let me make sure we're grounding this math in reality. If the number of tokens n grows quadratically with the side length of the image, and the attention cost grows quadratically with n, that means we are looking at a quartic growth curve.
Yes, exactly. To the power of 4.
So if a researcher decides they simply want to double their target image resolution, say from 256 to 512, their attention matrix doesn't just double. The sequence length quadruples. And because every token has to compare itself to 4 times as many tokens, the actual computation cost goes up by a factor of 16.
Precisely, a factor of 16. Doubling the resolution makes the math 16 times harder.
That's insane.
If you try to jump to a 1024 by 1024 image, you are looking at hundreds of millions of attention operations per layer. That is financially ruinous for a training run. A multi-million-dollar GPU cluster will simply choke out of memory.
It'll just crash.
Yeah, you absolutely cannot brute force your way out of Quartic complexity. This physical limit necessitates entirely new architectural paradigms. We have to design structured pixel-space diffusion transformers that can somehow cheat this math.
And researchers have basically developed a few distinct philosophies to bypass this compute cost while keeping the pixel-level fidelity intact. So instead of just listing off architectures, let's group them by how they actually tackle the math.
Good idea.
The first philosophy is the most obvious one, right? Just aggressively reduce the sequence length. This is the single-stream large patch approach seen in models like GAT.
Right, and the engineering behind GT is highly streamlined. If the sequence length is a problem, you just increase the patch size.
Simple enough.
Yeah. Instead of 16 by 16 pixels, maybe you use massive patches. This drastically shortens the token sequence, keeping the attention matrix manageable, and the transformer directly predicts the clean images. It supports end-to-end training without a VAE.
But wait, surely that defeats the entire purpose of moving back to pixel space. I mean, if your patch is massive, the linear output head at the end of the network has to somehow reconstruct all the complex internal high-frequency geometry of that specific area from just one single token.
This raises an important point, and you are spot on. It is an immense burden. Large patches inherently risk discarding the exact fine-grained details we abandoned latent space to capture in the first place.
Right.
So, to solve the burden placed on the output head, researchers moved to a second philosophy, which is explicitly dividing the labor.
Ah, okay. This is where we see local decoupled architectures like DP or Pixel-Dite.
Exactly. You acknowledge that macrostructure and microtexture require totally different levels of compute. You use a large patch diffusion transformer to model the global semantic layout.
So it gets the big picture.
Yeah, it gets the overall structure of the image correct at a very low computational cost. Then, operating in parallel, you deploy a lightweight detail module or a specialized small patch pathway to handle the local high-frequency textures. It explicitly separates the responsibility.
Which leads into another variation of this division of labor that I find incredibly elegant, which is frequency decoupled architectures.
Yes.
So models like Deco or spectral forcing. The way I understand this is that it mimics how a human painter actually works. Like, a painter doesn't start by rendering the exact microscopic texture of a single leaf in the corner of a canvas. They block out the broad, blurry shapes of the background first and only pick up a fine-tipped brush for the details at the very end.
That is a highly accurate way to visualize it because it aligns perfectly with the physics of diffusion. In the early stages of a diffusion process, the image is overwhelmingly dominated by Gaussian noise.
You just pure static.
Exactly. High-frequency visual components like sharp edges or textures are entirely drowned out by that noise. If you force the model to treat all frequencies equally from step one, it wastes massive amounts of compute and capacity trying to fit high-frequency noise that contains absolutely no real image signal.
So spectral filtering prevents that.
Yes. It applies a dynamic, time-dependent filter. It mathematically blinds the model to high frequencies early in the denoising process, preventing it from being distracted by the noise.
That's so smart.
It really is. This allows the network to focus entirely on building that robust, low-frequency semantic scaffold. Then, as the noise clears later in the timeline, the filter shifts, directing the model's attention to restoring the intricate, high-frequency textures.
That is brilliant. Now, the third philosophy for cheating the math takes a totally different route. Instead of changing the patch size or dividing the labor, it changes how a pixel is mathematically defined.
Right.
This is implicit neural field decoding, seen in models like PixNerd.
Yeah, and if we connect this to the bigger picture, standard vision transformers use a linear layer to map a token to a discrete grid of RGB values. PixNerd still uses large patches to keep the global token count low, but it completely changes the decoding mechanism.
How so?
Each patch token is interpreted as a conditional representation of a local implicit neural field.
Let me jump in with an analogy here for anyone who hasn't worked with neural fields. Instead of assigning a fixed color to a rigid, square grid of pixels, like a standard JPEG, a neural field acts more like a continuous mathematical function. You can plug in any exact X and Y coordinate, even the microscopic space between two traditional pixels, and the function outputs a color. It is the conceptual difference between a pixelated image and a scalable vector graphic.
That distinction is crucial because it decodes the patch pixels in continuous coordinates rather than discrete grids. The model can represent incredibly rich, scalable details while requiring far fewer global tokens to manage the attention matrix.
Wow, okay. And finally, we have cross-scale semantic anchoring, like the pDiT model. This basically acts as a tether, right?
Yeah, that's a good word for it.
It continuously connects the large-scale semantic tokens directly with the small-scale detail tokens. This ensures that when the detail reconstruction process is running, it can constantly query the high-level features so you don't end up with like a structurally inconsistent hallucination like a texture that looks like fur applied to a car tire.
Exactly. Now, all of these architectural acrobatics are strictly designed to navigate around the Quartic scaling law without resurrecting the VAE. But even if you implement these highly efficient structures, you run into a profound optimization wall that the authors identify as the learnability fidelity conflict.
Right, because we are back in the raw pixel space. Latents are low fidelity, but they are incredibly easy to optimize. Raw pixels give us absolute high fidelity, but they are brutally hard to optimize.
Brutally hard.
If you try to force a model to learn high-level semantic structures, like ensuring a generated human face actually has two eyes and a nose in the correct anatomical arrangement, purely from high-dimensional random pixel noise, the training process becomes incredibly slow and unstable. The state space of raw pixels is just too vast and chaotic.
It is an ocean of data. So to speed up that semantic convergence and give the model a lifeline, researchers started utilizing frozen vision foundation models, or VFMs.
Like DynoD.
Exactly. Models like DynoV2 or CLIP, and they are used as semantic guides through mechanisms like representation alignment, commonly called RBHE.
Okay, so how does this mechanism actually work in practice during a training run?
During training, you take your clean target image and pass it through a frozen, pre-trained DynoV2 model. DynoV2 analyzes the image and extracts high-level teacher features.
Okay.
Then, as your Pixel-Space Diffusion Transformer is trying to denoise its own noisy input, you apply a loss function that forces its internal intermediate representations to align with those teacher features. It basically gives the pixel model a strong, stable semantic target to aim for right out of the gate.
I have to push back hard on this. I see a massive conceptual trap here.
Let's hear it.
DynoV2 and CLIP are discriminative models. They are classifiers. They are explicitly designed to intentionally ignore things like texture, ambient lighting, and background noise, because those variables don't matter for object recognition.
Sure.
Like a golden retriever is a golden retriever, whether it is rendered in hyper-realistic 4K lighting or drawn with a crayon.
Right.
So if we force our pristine pixel generator to align its internal weights with dyno representations, Aren't we just reinfecting our model with the exact same discriminative biases? Aren't we just smuggling the VAE bottleneck back in through the back door?
That is the exact trap, and it is a severe vulnerability discussed at length in the paper. It is actually worse than just smuggling the bottleneck back in.
Oh, wow, really?
Yeah. Discriminative models create a many-to-one mapping. Thousands of images with wildly different textures, lighting, and pixel layouts all map to the exact same low-dimensional golden retriever teacher representation.
So what happens to the generator?
Well, if you force strict token-wise alignment, which is what standard RPA does, the high-dimensional pixel model quickly figures out the cheat code. It realizes it doesn't need to learn the complex physics of lighting and texture.
It just gains the metric.
Exactly. It takes an alignment shortcut. It learns just enough basic spatial semantics to satisfy the alignment loss function, and then it completely neglects learning the true fine-grained pixel-level distribution.
It's like a student who learns how to guess the right answers on a multiple-choice test without ever actually understanding the underlying material. The model gets lazy.
It gets profoundly lazy. The paper cites a study on Pixel-Repa, which proved that this strict token-wise alignment actually destroys FID scores Fréchet inception distance, the gold standard metric for image quality, in the later stages of training.
Destroy them, really.
Completely. It also crushes generation diversity. If you ask for 10 pictures of a dog, they all start looking structurally identical. You cannot just unconditionally take alignment strategies that worked safely in the latent space and blindly apply them to the native pixel space.
So researchers have to carefully calibrate that guidance. We need the semantic scaffolding, but we cannot override the model's pixel-level freedom.
Right.
But if we can solve these optimization bottlenecks, if we can truly master this raw pixel space, it gives us what the paper literally refers to as the holy grail of generative AI.
Yes, a genuinely unified multimodal architecture.
Because if you think about the history of ML pipelines, we have suffered from this severe granularity schism. Visual understanding tasks demanded abstract, invariant representations. Visual generation tasks demanded absolute sensitivity to spatial layouts and color gradients.
Two totally different languages.
Exactly. Because those needs were entirely opposed, we forced everything through fragmented, heterogeneous pipelines patched together with different tokenizers.
But when you operate in native pixel space, you remove the fixed pre-trained visual encoder entirely. There is no external tokenizer forcing its rigid vocabulary onto the data.
Oh, that's beautiful.
Right. Raw pixels, discrete text tokens from a language model, and specific task conditions can all be natively and jointly mapped into one single unified shared token space.
The paper highlights HyDream-O1 image as the benchmark for this. It is a single, unified transformer architecture that can simultaneously execute text-to-image generation, instruction-driven image editing, and complex visual reasoning, all without swapping out specialized encoders.
And the implications extend far beyond generating 2D images. When you scale the shared token space to video modeling, the potential is incredible, though the compute challenge goes completely supercritical.
Because of the frames.
Yeah. For video, your token count isn't just height and width. It is the number of frames, t, multiplied by the height, multiplied by the width, all divided by the patch size squared. The sequence explodes, and the model must guarantee temporal consistency in motion and physical identity across all those frames.
And it even extends to medical volumes, like 3D CT scans or MRIs.
Oh, absolutely.
You absolutely cannot use a lossy VAE on a CT scan because mathematically smoothing away a high-frequency detail could literally be the difference between a microscopic tumor being detected or completely erased from the image.
It's life or death in that context.
Literally. The paper mentions pixel puzzling diffusion models, or PPDM. They tackled a massive 3D memory issue by physically rearranging the spatial resolution into the channel dimension. It is a completely reversible operation that saves GPU memory without relying on any lossy compression whatsoever.
Which is non-negotiable for medical imaging. However, for the machine learning engineers listening who are actually implementing these systems, while the unified shared token space is the holy grail, it carries a severe localized danger that must be managed.
Okay, what happens under the hood when you force complex text understanding and raw pixel generation into the exact same transformer weights?
You trigger violent gradient competition?
Oh, yeah.
You have to consider the nature of the data. Language processing relies on abstract, discrete, symbolic reasoning. Pickle generation relies on continuous noise modeling and high-frequency spatial locality.
Completely different goals.
Right. If you force these two radically opposed optimization tasks to share the exact same computation paths and attention heads within the transformer, their gradients physically fight each other during backpropagation.
Meaning the math literally calculates updates that pull the neural network weights in completely opposite directions simultaneously.
Exactly. If you measure the local optimization relationship between the two tasks using cosine similarity, the value can frequently become negative. When gradients oppose each other that strongly, the model experiences catastrophic forgetting.
Just wipes it out.
Yeah, it will suddenly lose its language reasoning capabilities, or its image generation quality will inexplicably degrade. Having a shared token space does not automatically guarantee that understanding and generation are perfectly unified. Engineers have to meticulously allocate attention mechanisms and model capacity to prevent the tasks from cannibalizing each other.
So what does this all mean for you, the practitioner, building the next generation of models? The core takeaway here is that Pixel-Space Diffusion Transformers prove the industry bottleneck is actively shifting.
Yep.
It is no longer just a race for raw generative capacity. We are now navigating a highly complex Pareto trade-off between strict computational budgets, true multimodal unification, and extreme information fidelity.
Well said.
You shouldn't expect pDiTs to instantly kill off latent diffusion models for basic, everyday generation tasks, right? LDMs are simply too computationally efficient to disappear.
Oh, they'll stick around for sure.
But when your use case demands extreme fidelity like flawless text rendering, precise geometric structures, lossless medical imaging, and seamless unified reasoning, pDiTs are the absolute clear path forward.
The VAE was a brilliant, necessary shortcut that allowed the last generation of models to scale to the masses. But to reach the next tier of artificial intelligence, we have to take the training wheels off. We must confront the raw data manifold directly, regardless of the mathematical headaches it causes.
Which leaves me with a final provocative thought for you to chew on, straight from the implications of the paper's future outlook section. Currently, all of these modern architectures use fixed patch sizes and highly static computation paths. Every pixel gets processed. But think about how human vision actually works. When you walk into a room, your brain does not process a blank white plaster wall with the exact same granular attention and cognitive load as it does a highly detailed oil painting hanging on that wall.
That's a great point.
So, why should our models? What if the next massive breakthrough isn't just about finding clever ways to process all the raw pixels, but building truly dynamic token granularity?
Dynamic granularity, wow.
Right. Imagine a transformer architecture where the model autonomously decides frame by frame and time step by time step which specific pixels actually deserve your GPU's attention. Until then, keep building.